exponential functions, you might have seen a little of this before. It's one of those topics. It's in an Algebra 1 book, and if you have time at the end of the year, maybe you do a little of it, and maybe you don't. So.
We probably never did.
Okay. Okay. So if we just spent an entire chapter on exponents, what else can there be?
More exponents.
Well, okay. We're going to change what's up in the exponent. What were your what kind of exponents did you have last chapter? Numbers. You had 2, -2, 3 halves. So what have we? Variables, exactly. When you put a variable in the exponent and the base is a number. So the general form for an exponential is like that. B stands for base. The base is going to be a constant number. It's not going to be a variable. And the exponent will be your variable. So we're switching it up. Instead of having x squared, you're going to have 2 to the x power. But the good news is the rules of exponents that you learned about when to multiply them, when to add them, all that good stuff, that still works here as well. Because those rules work whether your base was a number or your base was a variable. So a classic example would be something like 2 to the x plus 4 power. That's an exponential function. Or I could do 7 to the 3x squared power. That's an exponential function. Got to have the base has to be a number, and the exponent has to have a variable in it. Now, they did, somewhere in the deep dark past, I'm not sure who actually set these, they decided they were going to put some restrictions on what the base numbers could be. So they said, all right, we're only going to have base numbers be positive numbers. So all base numbers have to be numbers greater than 0. They can't equal 0. You can't have 0 to an x power. Can't have -2 to an x power. It's got to be some number bigger than 0. But there's one number bigger than 0 that really wouldn't work very well as a base. 1. Why? If you start taking 1 to a power, what do you get? 1 to the second 1, 1 to the fifth 1, 1 to the 100,000th is 1. So it really doesn't do anything to have a base of 1. So yeah, they said we aren't going to have bases that are equal to 1 either. Okay, so I'm waiting for the question. Well, not negatives if it's greater than 0. But I always have people say, well, why don't they just say it's greater than 1 then? Yeah. Decimals and fractions between 0 and 1, a half, 2/3, 0.75. You can have those as bases. They're positive numbers, so they're greater than 0, but they aren't 1. So you can have the fractions in between there as bases. That's allowed. So that will keep haunting us as we come back to that. All right. Now, before I can do pretty much anything with exponential functions, you just got to see what the graph does. Because if you don't see what the graph does, you don't get why they're important. So we're going to graph these puppies. And the good news is it's awfully similar to what you were just doing. So, but you're becoming graphing experts. I don't want that there. You're going to be amazing graph experts. Okay, we're going to graph the most basic, simple exponential function I can give you. 2 to the x. I can't give you 1 to the x. And I certainly don't think doing some fractions would be a good thing to start with at first. So 2 is about the smallest base number I can give you. And once again, to get you to see why it does what it was, we're going to do everybody's favorite, the d-table. And we'll try graphing our usual about 0, 1, 2, 3 and see if we can see what's happening. But this time you have to realize when you sub a number in for x, if I'm putting 0 in for x, where is that 0 going? It's the exponent. So you have 2 to the 0 power, which would be 1, yes. And 2 to the first power is 2. So then we'd have 2 to the second power, and 2 to the third power. Okay, so what's happening to those y coordinates? They're doubling. The next one's going to be 16, then 32, 64. These y-coordinates get big fast, so we won't be plotting many points. So now, if the base was 3, what would those y-coordinates do? They would be tripling every time. So the bigger the base number, it makes the y-coordinates go up even faster. They get really huge, really quickly. So we're going to graph that much and see what it looks like. If I plotted 0 over and 1 up, I'm starting from the usual basic origin here. 1 over is 2 up, and I just keep doubling it. Then 4 up, then 8 up. Looks like a nice little curve. But probably what do I need to graph to really finish this off? Yeah, I need to do the other side. I got to do negatives. So we better try maybe -1, -2, -3. And here comes your exponent rules. Wow, amazing here. If you put -1 up there and you have 2 to the -1, what's that the same thing as? What do you do with negative exponents? You move them to the opposite side of the fraction. So that is 1/2, yeah. So if you see a negative exponent, you're going fraction. So 2 to the -2. Yeah, because you would do 1 over 2 squared. You drop it to the bottom. And then, yeah, that's really 1/4. So 2 to the -3 is going to be 1/8 when we drop it to the bottom. Okay, so what's happening to those y-coordinates? They're shrinking, yeah. The denominator is doubling every time. So 1/2, 1/4, 1/8. Is it going to be fun to plot this? Particularly on your tiny squares. I have enough trouble on my squares, let alone on your squares. So I said, well, right now I'm going to plot them and be accurate, but after that you won't be plotting these fractions because you'll see what happens. But I have to be a 1/2 up, then a 1/4, then an 1/8. What's it doing? If I keep going, it's got to be a 16th. It's basically going to be a straight line. Is it going to cross the x-axis? It's not going to cross the x-axis. The fractions will get smaller and smaller and smaller. I'll eventually have 1 over 512, 1 over 1020, 1024. They're going to be tiny, tiny fractions, but there's still going to be something above 0. So it's not going to cross the x-axis. So what's that mean the x-axis is? It's going to keep getting closer to it, but it's not going to cross it. Hit them before Christmas. Asymptote! Yes, you got that. It was a one-time thing with hyperbolas, no such luck. It keeps getting closer and closer, and the x-axis is an asymptote. So you're going to have to draw a dotted line every time, and the graph keeps getting closer and closer to it, but theoretically does not touch it. If it gets to infinity, it will touch it. So that's kind of an interesting curve. I mean, it looks like it's so flat, growing in such small increments on the far left, and then zoom, it takes off. And that is what we call exponential growth. You may have heard, if you were listening to the news, they may have said, the population of China is growing exponentially. Or, unfortunately, gas prices, we don't want them to grow exponentially. That would be really bad. But sometimes that happens. So many, many things in the real world grow exponentially. We'll eventually get to some science applications. If you start out with a few bacteria and they reproduce and double themselves every 2 hours, how many will you have after 24 hours? Well, that's exponential growth if they're doubling themselves each time. So predicting how fast that, if there's a spread of some virus, how fast is it going to spread? That can be done, modeled with an exponential curve. So I can't tell you how many tons of uses there are for exponential functions. By the way, this is the one chapter come test time you all will be begging me to put word problems on the test. Because you'll say, those are the easiest ones. I not lying to you. At the end of this chapter, you're going to tell me, please give us word problems. You will. So, but this really is something that is not, once we get into more details, I can actually show you what the real world cares about this a lot. Okay. So obviously though, if that's what a basic exponential function looks like, I'm not going to do just that. All the rules we know about shifting them, flipping them, all that stuff still applies. And in particular, I want to look at one special situation. What if I had changed that to a 1/2 to the x instead of a 2 to the x?
Your negative.
Okay.
Your negative would be like 1, 2, 4, 8, and your positive would be a half.
Okay. So JC's saying these would have switched. When we had 1/2 to the first, we would have gotten a half. 1/2 to the second power, we'd have gotten a fourth. And she's right. It would have switched them. So it would have made the two sides switch places. So we'd be following the asymptote over on the right-hand side, and the rising part would be on the left-hand side. Well, I want you to note why. Isn't 1/2 the same thing as 2 to the negative 1 power? Okay. So if that's to the x, then can't I just say that that's 2 to the negative x power? So when you see a 1/2 to the x, it's the same thing as 2 to the negative x. Which one's going to be easier to plot points for? 2 to the negative x. If you've got an icky fraction, just bring it up. It'll be easier to graph with. And yeah, it's just going to flip it. Just like, let me remind you, do you remember when we were graphing square root the other day, and I reversed it on you, and I gave you 6 minus x? Our square root normally went off to the right. What'd that negative on the x make it do? It went left. It flipped it over the y-axis. Does the same thing here. It flips, takes that graph, it's a negative x, and it makes it flip. So the asymptote's still in the same spot. Asymptotes, can you see that color? Or should I change? Asymptote still on the x-axis. You're going to use that exact same t-table, except you're going to plot it on opposite sides. When you do the 0 over 1 up, okay, that's the same. But when I go 1 over 2 up, I'm going to go to the left side, I'm going to go 1 over and 2 up. And then 2 over and 4 up, 3 over 8 up. So my curve is going to be on the left side, and I'm going to follow the asymptote down the right side. If that side was exponential growth, want to guess what they call this side when it's falling? They call this side exponential decay. It's coming down. It's losing value each time exponentially instead of gaining value. So that's a decaying situation. Have you guys ever talked about radioactive elements and half-life in any of your science classes? No? Okay. Something that's radioactive, an element that's radioactive decays over time. And in fact, it cuts itself in half. Different elements have different half-lives. So they may say the half-life of this one is 500 years. That means in 500 years it cuts itself in half. And in another 500 years it cuts itself in half again. And in another 500 years it cuts itself in half again. That would be the same thing as this, a base of a half, and it would be decaying. Thing is, it never completely is gone, because it never gets to 0, but gets down to this very, 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 very small amount. We'll do some problems later on. When they like find a fossil, have you ever wondered how they figure out how old it is? And when they find human bones, how do they figure out how old it is? We just trust the science, right? But the science has the math. And they actually know it has an element, human living organisms have an element in them called carbon-14, which decays over time. we know how much carbon-14 is in a live human. When they find these ancient bones, they can measure how much carbon-14 is in those bones, and then they can use actually one of those equations on your sheet there and figure out how old the bones are. It's an exponential function. Yeah. So exponential decay has a lot. Okay. So there's two ways you guys can see exponential decay. If your base is a fraction, you're going to have exponential decay. Or if you have a number to a negative exponent, it's going to decay. So there's two ways to get exponential decay. Hint, that's a journal question. So I'm going to go back now and ask you a few. I just want you to tell me, I'm going to write you some equations, tell me if it would be growth or decay. So if I gave you 7 to the, that was supposed to be 3 plus x, is that going to grow or decay? Grow, yes, that's growth. It's a base, it's not a fraction, it's a number, actually I should tell you, if the base is greater than 1, it's going to grow. If the base is a fraction between 0 and 1, it will decay. So that one's going to grow. What if I gave you 1/3 to the 2x power? Decay because it's a fraction, you're going to bring it up, it's going to be 3 to the negative 1, you're going to have negative exponent, so that's going to decay. It's between 0 and 1, so it will decay. Okay, what if I gave you .36 to the 4x power? So if you can have decimal bases, it's a little weird, but you can have it. Yeah, it's a number bigger than 1. It's going to grow. All right, what if it was 0.635 to the x minus 7 power? Why? The decimal between 0 and 1, x is a positive power, so yep, that's going to decay. Okay. What if I had given you 5.8 to the 3 minus x? Why decay? Okay. The base is big enough, it's greater than 1, but the x is negative, it's going to decay. All right, here's your challenge problem of the day. What if I gave you 1/8 to the negative x power? Essentially, yeah. The 1/8 would make you think it's decaying, but it's also got a negative power on it. So it's like having two negatives. Two negatives together make a positive. Another way you can think of it, that 1/8 is 8 to the negative 1, and if it's done to the negative x, the two negatives make a positive, and so, yeah, it actually is growth. So that can happen. Okay. Lovely, right? Well, we need to graph just one other thing now. Geez, you think we could shift these off of being centered at 0, 0? Of course you can, because it shifts with the exact same rules you already know. Isn't that good news? You don't have to learn anything new. So suppose I said graph 4 to the x plus 3 power minus 8. Okay, so from now on, when you see you have things added and subtracted in there, you have to go, okay, it's shifting. What happens when you change x to a quantity? Which way does it shift? If you do x plus a number, x minus a number, that's always your horizontal shifting. So do you go with the positive 3, or do you switch the sign on this one? Yeah, when it's with the x, you switch it. So it's going to go left 3. Okay, the minus 8's on the end out there by itself. So that's just like normal. Yeah, that's the up and down, and and you go with the sign it has, so this is a down 8. So we're going left 3, down 8. That's going to be your new origin. Okay. So then on these functions, you have to remember, there's something special that goes through the origin whenever you graph an exponential function. Well, part of that graph always goes through the origin. If I bounce back. Here's the origin. What's going through it? That asymptote always goes through the origin. So when you shifted it, that's where your asymptote goes. We know right now we got an asymptote down here at -8. So as soon as you shift it, boom, put your asymptote on there. Then you're going to have to plot some points. Sorry, but remember, you've already taken care of the +3 and the 8, so when you're plotting points, you're just plotting plain old 4 to the x. The 3 and the 8 we've handled with where we shifted it to. So you just have to figure out what's 4 to a few powers. Okay, so you're not going to be able to go very big here. So if you try 0, 1, 2, 3, what am I going to get? 4 to the 0 is 1. 4 to the first power is 4. 4 to the second power, and 4 to the third power? 64. Okay, who wants to count 64 boxes? We aren't grabbing it, baby. No way, no how. Oh, shoot, I'm way over. Yeah, cool.